Werner Heisenberg introduced the uncertainty principle in 1927, establishing a strict limit on what we can simultaneously know about a quantum system. That principle is formalized by this equation. Delta Q times delta P is greater than or equal to 1/2. If you take an undergraduate physics course anywhere, you'll be taught this specific inequality is the precise, unshakable mathematical proof of quantum uncertainty. Historically, physicists like Niels Bohr justified this principle using concrete thought experiments, most notably the diffraction of particles through single and double slits. But there is a glaring problem. It is a mathematical fact that this standard equation completely fails to derive the outcomes of those thought experiments. This is a rigorous mathematical failure of standard deviation as a geometric measure of wavefunctions. The math is supposed to prove two central claims. First, that you cannot have an arbitrarily sharp specification of both position and momentum. Second, that if you determine the path of a particle in a double-slit experiment, you destroy its interference pattern. In 1985, physicists J.B.M. Ufink and J. Hilgevord published this paper in the Foundations of Physics, systematically exposing the inadequacy of the standard equation. Look at equation 3 on this page. By definition, standard deviation, or delta Q and delta P, measures the spread of a probability distribution around a mean. To understand why this universally accepted metric breaks down, we have to look exactly at how standard deviation behaves when we calculate the actual probability waves of particles passing through slits. Figure 1 outlines the basic setup for single-slit diffraction. We want to measure the position, Q, and the momentum, P, of a particle right at the screen. The probability densities for this setup are shown here in Figure 2. Position is a localized square wave matching the width of the slit. Momentum is the Fourier transform of that, a sinc-squared function. Notice that the vast majority of momentum probability, roughly 95%, is sharply localized within that central peak. Now we calculate standard deviation for momentum. By definition, probability density is multiplied by p squared. This creates massive mathematical distortion. The p-squared multiplier gives enormous weight to the vanishing tails of the momentum distribution. Even though the tails contain almost zero probability, they fall off too slowly to counter the p-squared multiplier. As a result, the calculation of delta p diverges to infinity, regardless of how wide or narrow the slit is. The math claims the momentum is completely uncertain. It ignores the reality that 95% of the probability is localized right there in the center. In the double-slit experiment, standard deviation reveals a different mechanical limitation. Look at the top graph of Figure 3. The position density shows two distinct Gaussian peaks, representing probabilities of passing through either slit. Moving to the bottom graph, the momentum density forms an overall envelope containing a series of high-frequency oscillating interference fringes. When we apply standard deviation to this distribution, delta P simply measures the total macro extension of the entire pattern. It calculates the width of the outer envelope. Imagine two theoretical states, one intact with sharp interference bands, and one where those bands are smoothed out. Delta P only measures the outer edges, so its value remains identical. It is completely blind to the internal fine structure. Bohr's argument dictates that knowing the particle's path destroys the fringes, but standard deviation cannot prove that destruction because it cannot resolve the fringes themselves. To accurately express the uncertainty principle, we must discard standard deviation entirely. We need a new geometric vocabulary that captures both the macroscopic boundaries and the microscopic internal structures of wavefunctions. They introduced an exterior measure, mathematically defined here in equation 13 as the overall width, or W. Conceptually, overall width is simple. It is the length of the interval that encompasses the vast majority of the total probability, cutting off the diverging tails. Next, they defined the interior measure, called the mean peak width, or lowercase w. To extract this interior measure, we look at Figure 4, which plots an autocorrelation function, g of q. Think of autocorrelation like sliding a wave over a copy of itself. The graph tracks how quickly overlapping probability drops. The mean peak width, w, is defined as that drop-off point, measuring the average width of the internal fringes. We now have two independent parameters, an exterior bound telling us where the system is, and an interior bound defining its sharply resolved internal structure. This brings us to Uffink and Hilgevort's rigorous formalization of the uncertainty principle, seen here in equations 24a and 24b. The new mathematical law states the mean peak width of one variable, multiplied by the overall width of its conjugate, must be greater than or equal to a constant. This pairs an interior micromeasure with an exterior macromeasure, creating a constraint Heisenberg's original formula missed. Mechanically, this means if you compress the exterior macroscopic boundary of a particle's position, you inevitably force the interior fine structure of its momentum to expand and blur. We can finally apply this to Bohr's double-slit puzzle, determining which slit the particle passed through by measuring the microscopic recoil of the photographic plate. To detect this tiny recoil, the photographic plate's initial momentum needs a strictly bounded overall width. In the new uncertainty relation, the math reacts immediately. As the plate's overall momentum shrinks, the mean peak width of its position is mathematically forced to expand. Physically, an expanded mean peak width means all positions of the photographic plate within that wider region become equally probable. Because this uncertainty region is now larger than the distance between the individual interference bands, the exact location of the impacts becomes entirely unpredictable. The fringes bleed together, washing out the pattern. By abandoning standard deviation and linking the macroscopic momentum boundary of the screen to its microscopic position resolution, we have finally proven that knowing the particle's path must obliterate the quantum interference pattern.